Hello everyone. Now you are going to solve an example for the solar concentrators. Okay, example is applied for internal force of convection. Okay, here we have the solar concentrator. You can see the concentrator here. So these are also called the troughs. Okay, so this one is trough, and it is shaping parabolic. Okay, therefore it is also called the parabolic trough. What happens is that you have solar flux. So the solar heat can be parallel or it can be cannot be parallel. Okay, it depends, but most of the time we assume that it is parallel. Okay, these parallel rays are falling on these concentrators or reflectors and then reflected back to this tube. Okay, this one falls and reflected back to here, this one falls and reflected back to here. Okay, this one falls and reflected back to here. So it means that this tube, you can see the length of the tube is located such that it is at the focal length of the trough. Okay, this reflector, it is at focal length of the reflector. Therefore, whatever ray comes on that reflector is bounced back on this tube. Okay, therefore, this tube gets hotter. The fluid inside the tube gets hotter and hotter. The amount of heat flux is 20,000 watts per meter square, and it is constant. And the concentrator fluid have the density, and it has the conductivity, specific heat value, and the viscosity. The diameter of the tube is 70 millimeters, so you can see the tube here. It is 70 millimeter with a diameter, and the mass flow rate is 2.5 kilograms per second. So yeah, the mass flow rate is, if I say that this part is inlet, okay, and if I say that this part is outlet, and then you will have the direction of the flow as this one, and that will be 2.5 kilograms per second. And the mean inlet temperature is, this one has a temperature of 400 degrees Celsius and this one has a temperature of 450 degrees Celsius. Find required lengths, what length is required for this temperature change, what is the amount of heat transferred to the fluid, surface temperature of the tube, and this is the second part. Let's first see the cycle. So here you have the concentrators, you see the concentrators, here you have the hot part which is 450 degrees Celsius, and here you have the cold part which is 400 degrees Celsius. As the fluid comes, it is sent to heat exchanger. In heat exchanger it gives off its heat and heats another fluid of the cycle. Okay, and this fluid is getting hot here, so this part is hot and this one becomes cold. It gets hot and is sent to turbine. It rotates the turbine to get electricity, and the question says that the 20 megawatts of electricity is generated, so 20 megawatts, and the turbine inlet temperature is 430 degrees Celsius, so you have the 430 degrees Celsius, and the outlet of the condenser is 40 degrees Celsius. So this one is the condenser. Okay. The outlet of the turbine is sent to condenser, and there it gives off its heat again. This is the requirement of the second law of thermodynamics, or you can say the requirement of the pump, because turbine outlet is two-phase and the pump cannot handle with the two-phase fluids, therefore you should send it to the condenser. Or the second law of thermodynamics requires that if you have some heat input, you should also have heat output. This is the second law. And therefore here you have the heat output, and then set back the pump, and then from the pump again back the turbine by the heat exchanger, and says that outlet of the condenser is 40 degrees Celsius. Here you have 40 degrees Celsius. And then what number of concentrators required for this electricity power? This is the last part of the question. Now let's solve the question. Firstly, so if I use a different color here, so this color, so whatever sun flux that falls in this tube, so whatever sun flux that falls on that tube, it heats the surface of the tube. Write it here. This is the tube. Okay. You have the sun flux everywhere. Okay. And due to sun flux, this surface becomes hot. Ts, hot. And inside that tube, you have the fluid. And out of the tube, you have the fluid. Okay. This fluid has some enthalpy in, because it's an open system. It has also enthalpy out. Whatever energy that comes from the sun, it heats Ts. Okay, it heats Ts and Ts becomes hot. Since this Ts is hot, the fluid becomes hot. Okay, from that tube surface you have the energy that comes to the fluid. Okay, it is by convection. Why it is by convection? Because you have the fluid that moves inside the tube. Okay, so fluid moves, therefore this energy from the surface of the tube into the fluid is convection. Okay. Now what I will do now, I will write the first law of the thermodynamics as always. So in is same as out, since it is steady. Okay. First law. So the sun energy is Q dot AS. So sun energy is Q dot S. It is flux. Okay. Therefore you should multiply with the area. Q dot S into AS, surface area, should be equal to this convection heat transfer. If you assume that there are no any losses, whatever energy that is coming from the sun is converted to convection energy inside the fluid. Therefore, these should be equal to each other. Q dot S AS should be same as Q dot CV AS. So from here, I say that these are cancelled out. Is same as Q dot CV. Okay. And I know the Q dot AS value. I can write the Q dot CV as H into Ts minus Tm. Okay. In this problem, Ts is function of location, because here you have different surface temperature, here you have different surface temperature, and here you have the different surface temperature. Therefore, Ts, this one is function of x. Okay. And now this one is unknown. Ts is unknown. And also H. For convection problems, H is function of Reynolds number and the Prandtl number. It is for internal convection and external convection. For natural convection, it will be a bit different. So here it is function of Reynolds number. Reynolds number is rho v d by mu. Okay. And Prandtl number. I can find Prandtl number from the question. Prandtl number is mu by alpha. Okay. And I can find the rho. Rho is given in the question. It is 700. Diameter is given. Okay. And velocity I can find. How can I find the velocity? Velocity will be m dot by cross-sectional area. Okay. I know the m dot, cross-sectional area into density. Okay. I know the m dot, that is 2.5 kilograms per second, and I can find the velocity. Okay, if I find the velocity, I know the Reynolds number, I know the Prandtl number, I can find the H value. If I know the H value, this part is okay, and I can apply this equation for the outlet. Okay, this one is outlet. Okay, I can apply this equation to the outlet. I can then find the temperature at outlet, because I know Tm at outlet, that is 450 degrees Celsius. Okay, therefore I can find Ts at outlet. This part can be solved easily. Okay. Now comes the second part. It says that find the required length and transferred heat to the fluid. So now I should apply the energy balance again, but now energy balance will be that you have heat into the system, that is heat is convection inside the system. That convection heat transfer changes the enthalpy of the system. If I write the energy for the total system, so you will have again total in should be total out. Okay, you have the convection energy into the system with some area plus enthalpy at inlet. Okay, these are the in quantities. This one is in and that one is in, should be equal to m dot and enthalpy at outlet. Okay, this is the second part. From here, what I can find is that if I write the equation in full form, so you will have QCV. Okay, QCV is exactly the same as QS, I know it. Okay, and AS is pi dl, surface area of the tube. So if you go back to here, this is the surface area of the tube. You have the length from here to that point, and they also perimeter. Pi dl, so m dot, I know it, I don't know L, this one is unknown. Okay. I know enthalpy in, so this one is Cp, temperature at inlet. I know enthalpy out, that is Cp, temperature at outlet. Now from here I can find the length of the tube, because this is the only unknown. Therefore you see that this part is solved, this part is solved. And now the last part says that transferred heat to the fluid. Transferred heat to the fluid, if you see the equations, it can be Q dot S into AS, surface area, or Q dot CV into AS, surface area. They are the same stuff. But this is the transferred heat to the fluid, or it can be the enthalpy change of the fluid, because whatever heat is transferred to the fluid, it changes its enthalpy. If I know the enthalpy out, I know it. If I enthalpy in, I know it. If I multiply with the m dot, I will get the energy transferred to the fluid. This is the last part, energy transferred to the fluid. Okay, it will be either, okay, so one is that Q dot S AS, that is, since that is equal to Q dot CV AS, or it is m dot enthalpy at outlet minus enthalpy at inlet. Okay, all of the equations will give you the same result. Okay, so we have solved the first three parts. Okay, now let's solve it and finish the problem, and then move on to the next part of the problem. I will solve the problem in Excel because it will be easier for the Reynolds number to the power of 0.8. Okay, it is easier to deal with in Excel. So let's write the values here. So I have Q dot S, which is 20,000. Write that 20,000. Okay, and also have the rho, which is 700. I have the K value, which is 0.78. I have the Cp, which is 2590. I have the mu value, which is 0.15 E minus 3, and I have the diameter 70 E minus 3. I have the m dot, which is 2.5, and I have the inlet, which is 400. I have the T outlet, which is 450, and then I have the TL, which is 40 degrees Celsius. Okay, let's keep it for the end of the problem. Okay, now let's solve the problem one by one. So I will first find the required length, and then transferred heat and the surface temperature. Okay, we'll solve it one by one. So for the first part, I should find Q dot CVAS. Let me write it here. So you will have L will be equal to m dot enthalpy out minus m dot enthalpy in divided by Q dot CV into pi d. Okay, let's write it. So first the enthalpy in, it will be m dot, which is here 2.5, into Cp and into temperature at inlet. Enthalpy out, this one is rate of enthalpy out actually, but we are writing enthalpy out 2.5 into Cp and into temperature at outlet. Okay, so I should subtract and divide by Q dot Cv. I write Q dot Cv, that is exactly equal to Q dot S. So from here I will get L, it will be this one, H out minus H in divided by pi into the diameter. And Q dot Cv also, there should be Q dot Cv here. So if I multiply with Q dot Cv value, okay, and you have the 74 meters. Okay, the L is, this one is 74 meters. I have finished the first part. Now comes the second part, transferred heat. As we have said, it is Q dot SAS, Q dot CV AS, or M dot H out H in. You have the same results if you apply any of it. So therefore I will write it as Q dot transferred heat, that will be equal to enthalpy out minus enthalpy in. That is this transferred heat to the fluid. Yeah. It's 300 kilowatts. And now comes the surface temperature at the exit of the tube. For that one, I will need this equation. I should first find the H, Reynolds number, and Prandtl number, and then I will find the Ts value. And to find the H value, for internal forced convection, if you remember, H starts at the highest value and then drops and gets its constant value after FTF. This part is FTF, fully developed flow. After fully developed flow, it gets its steady constant value. Okay, firstly, I should check that if you are in fully developed flow part or not. Okay, for that case, check in FTF or not. Okay, for that one, I should check if it is laminar or turbulent. Okay, so therefore I should find. So therefore check. So this one is the one. So 1A. Check laminar or turbulent, because I have different equations, okay, for laminar and for turbulent. First let's check if it is laminar or turbulent. I should find the Reynolds number. Erase this. So the Reynolds number, it will be rho Vd by mu. Okay, rho Vd by mu. I don't know V, let's find the velocity here. Velocity will be m dot divided by cross-sectional area. I should find cross-sectional area, AS. AS will be pi into diameter squared by 4. This is the AC. And then you will have the velocity, which will be m dot divided by cross-sectional area multiplied with the density. This should be in brackets, and the velocity is 0.93 meters per second. I know the velocity and I can find the Reynolds number. It will be density into velocity into diameter divided by the mu value. And Reynolds number, as you can see, it is much greater than 2300, so Reynolds number is greater than 2300, therefore it is turbulent. Okay. For turbulent flow, if you need to know if it is fully developed flow or not, you should divide the length by diameter. Okay, and this length by diameter should be greater than 10. Okay, if it is greater than 10, then it means that if you are in fully developed flow, then there is no problem. Let's check it. So L over D, it will be length 74 meters divided by the diameter. Okay, 1.05 e to the power of 3. It is exactly greater than 10, and therefore we are in fully developed flow, therefore H value is constant. Okay. Good, now let's go back to our equations here. For fully developed flow, we have this correlation. Okay. For fully developed flow, we have this correlation for turbulent flow. But we have different Dietz-Bolter, Seidel, Tate, Binlensky, okay. There are lots of correlations, but we will use the easiest one, which is Nusselt number 0.023, Reynolds number 0.8, Prandtl number to the power of n. If it is heating, n is 0.4. If it is cooling, n is 0.3. Okay. Let's first calculate the Prandtl number. Okay, Prandtl number will be nu by alpha. Okay, nu is mu by rho, alpha is k by rho Cp. Therefore, it will be rho Cp by k, and then it will be mu Cp by k. This will be the Prandtl number. Let's find the Prandtl number. It will be viscosity into specific heat value divided by the conductivity. This is the Prandtl number, and the Nusselt number will be 0.023, Reynolds number 0.8, Prandtl number n. Okay, and in our case it is heating, therefore n will be 0.4 because we are heating the fluid. Now the Nusselt number, this is average Nusselt number, it will be 0.023 multiplied with Reynolds number to the power of 0.4, Prandtl number to the power of Reynolds number is 0.8, Prandtl number is 0.4. Okay, this is the Nusselt number that we have. 1000, it's about 1000, and then I will find the H value, because I know that Nusselt number is H L by K. Okay, so if I know it from here, H value will be Nusselt in the K by L. Okay, let's find it. H bar, it is average H, therefore we are writing H bar. It will be Nusselt number multiplied with the K and divided by characteristic length. Okay, this one is characteristic length. L characteristic and L characteristic. And for the pipes, characteristic length is the diameter. And this is the H bar value. Okay. Now, as we have found the H bar value, now we have solved the problem almost. So you will have, we have the H, this one is H bar, average H. I know the Tm at outlet, I can find Ts at outlet. So it will be Ts at outlet will be equal to Q dot Cv divided by H plus Tm at outlet. Okay, let's find it. So Ts out will be QCV, Q dot Cv divided by H value plus Tm outlet, this one. Okay. Temperature is 466 degrees Celsius. This is the surface temperature at the outlet of the pipe. If you go back to here, the temperature at the surface here it is 466, but fully temperature is 450 degrees Celsius. We have 15 degrees Celsius temperature difference, therefore we have the heat transfer by convection. So we have finished the first three parts, and let's do the last part and finish the example. For the last part, it says that we have condenser here, 40 degrees Celsius, we have the turbine inlet temperature and the turbine power. So the question says how many collectors or concentrators required for this electric power. Okay, if you know from the thermodynamics, this says that minimum means that you should have the maximum efficiency. So if you know from the first thermodynamics, the maximum efficiency is given by Carnot. Okay, if it is heat engine, so this one is the heat engine, because we are generating power. Heat engine, we have the Q dot H to that heat engine, you have Q dot low rejected heat, and you have the work dot out, work done. So work dot out divided by Q dot H, that is the definition of the efficiency. Instead of work dot out, I can write Q dot H minus Q dot L by the first law, Q dot H minus Q dot L divided by Q dot H. Okay, and that will be by Carnot efficiency, 1 is the TL by TH. Okay, this is the meaning of the efficiency. So I know the TL, this is the lowest temperature here, it is 40 degrees Celsius. I know TA, it is the highest temperature, it is 430 degrees Celsius. Okay. Then from this temperature difference, I can find the efficiency. But these temperatures should be in Kelvin, because if you divide the temperature, there should be in Kelvin. Let's find it. Eta max will be equal to 1 minus, we should convert the temperature, which is, let me write the temperature values here. TL is 40 and T high is 430 degrees Celsius. So eta max you'll have 1 minus convert temperature, which is TL from Celsius to Kelvin, divided by, you should convert temperature again from Celsius to Kelvin. We have the efficiency. Efficiency is 55%. Okay, then it means that whatever heat is coming to the system, you are converting 55% into work output as an electricity here. So therefore, I can write this one as Q dot H will be equal to work dot out divided by eta. Okay, since this Q dot H is provided by the concentrators, because concentrators are giving off the heat, therefore this one divided by Q dot of one concentrator will give you the number of concentrators. Okay, let's find first the total Q dot. Okay, Q dot total, it will be work dot out, which is 20 megawatts. Let's write it, work dot is 20 megawatts. Therefore Q dot total will be this one divided by that one. This amount of heat should be provided to get this amount of power. That heat will give you the number of concentrators. Okay, the number will be this one divided by heat transferred by one single concentrator, and you have 111. Okay, at least because this is the maximum efficiency, at least 111 concentrators we need for getting this amount of power. Okay. So this is the end of the example. Okay. Now we'll solve the next example for the next video. Okay. Best wishes.